In the previous video, we were introduced to the idea of energy transitions and spectroscopy, and in this video, we will begin to focus on IR spectroscopy. Infrared spectroscopy is based on bond vibrations because energy in the infrared region is the correct energy to be able to cause a molecule's bonds to stretch or to bend. So we can think about a bond kind of like a spring. So there may be an ideal bond length for any particular carbon-hydrogen bond or carbon-oxygen bond, but there is the ability to stretch. If we have a molecule, let's say the carbon is connected to two hydrogens and some other things, well, there is an ideal bond angle, but this bond can also bend, resulting in smaller or larger bond angles. Infrared radiation will be absorbed by a molecule when the particular photon of energy matches the energy required to do a stretch or to do a bend. So there are several types of stretching vibrations. And so if we think about our central atom and then two other atoms connected to it, they can stretch so that both bonds are lengthening at the same time. This is called a symmetric stretch. Or they can stretch so that one is getting shorter while the other's getting longer, then that one gets shorter as the other one gets longer. This is antisymmetric stretch. In terms of bending vibrations, there are a couple of in-plane bends. So if this hydrogen, carbon, hydrogen are in the plane of the screen, then they can bend while remaining in the plane of the screen. So if they both bend away from each other, or they could both bend in the same direction. So this first one is called scissoring, and the second is called rocking. We also have out of plane bending. So now we've moved our molecule perpendicular so that this is coming forward, the carbon's in the plane, and this is going back. And so if we think about these in a plane that is perpendicular to the screen, they can both go down and back up together, or one can go up while the other goes down. This one is called a wag, and this one is a twist. Now, molecules will absorb a particular energy to cause a stretch or a bend. But let's also think about if we were to compare a carbon-carbon single bond, a carbon-carbon double bond, and a carbon-carbon triple bond. A single bond is going to be weaker than a double bond, which in turn is weaker than a triple bond. So if we have bonds of different strengths, we would expect that it takes more and more and more energy to be able to cause that bond to stretch. So recognizing that different bonds require different energies, if we observe a particular energy, then we know what bond type we have present in the molecule. And so that's how we can use IR spectroscopy to give us information about bond types that are present in a molecule. So here we have a portion of the electromagnetic spectrum, and this is the overall infrared region, which goes from about 10,000 to 100 inverse centimeters, but the useful region goes from about 4,000 to 400 inverse centimeters. And you'll probably recognize that from running your IRs in lab as well as looking at IR spectra. So let's take a look at this sample spectrum. And first of all, notice that we're looking at percent transmittance over here. If there is high transmittance, that means that the infrared radiation is not being absorbed by the molecule, and instead it reaches the detector. Then where we have dips, this is where the molecule absorbs that particular energy of the infrared radiation, causing a bond vibration to happen. Now, even though these are dips, we can still call them peaks. So here we have no absorption because the energy of the photons do not match the energy required to stretch or bend a bond. Here we do have absorption because the energy that's being applied matches the energy to stretch. At this amount of energy, again, there's nothing absorbed, but now there is energy being absorbed, causing different types of bond vibrations. Now, if we look along this axis, we can see this is given in wave numbers in inverse centimeters. So wave number has the symbol nu with a bar over it, and this is equal to 1 over wavelength. Now remember that energy is inversely proportional to wavelength. Another way to say that is that energy is directly proportional to 1 over the wavelength. So in other words, energy is directly proportional to the wave number. So that means over here, we're talking low energy because it's low wave number. And over here, it is high energy because it's high wave number. Typically, you'll be looking at a spectrum from about 500 to 4,000 inverse centimeters, but we want to focus on different regions of the spectrum. So around 1500, this is the dividing line between the major group over here. This is called the diagnostic region. This is where we're going to see absorptions that are very characteristic to different bond types. And then this area is called the fingerprint region. There are some useful signals that we're going to see in here, but typically we consider the fingerprint region, as its name suggests, as a fingerprint of a particular molecule. So this can be used in comparison with a spectra of a known compound, just like your fingerprints at a crime scene. So we will focus on the diagnostic region and also take a little bit of a peek at the fingerprint region. And finally, we can think about some different zones within the IR spectrum. So from around 2700 up to 4000, this is where we have bonds to hydrogen. Around 2100 to 2300, this is where we have triple bonds. Here around 1600-ish to 1800, here we're looking at double bonds. And then down here, we are looking at single bonds. And this all refers to stretch. So this is a something hydrogen stretch, triple bond stretch, double bond stretch, single bond stretch. The bending vibrations that I'm aware of are also down in the fingerprint region. As we're looking at an IR spectrum, so far we've been talking about seeing peaks at particular wave numbers corresponding to the energy that matches the bond vibration. But we're also going to look at differences in the strength of the signal. So these signals are kind of short, they don't dip down very far. This one is long, it dips down much further. So this one is a weaker signal and this one is a stronger signal. There's also going to be some features in terms of how broad or sharp a peak is. So all of these are pretty sharp signals, but we are going to see a few that are more broad. So there are several characteristics of peaks that we need to consider as we are interpreting IR spectra. Here we have a table of IR values. This is taken from McMurray's Organic Chemistry 10th edition. And it lists a variety of functional groups and just bonds, and it gives the common absorption range and a little bit about the characteristics. I will provide this on quizzes and exams, so you don't have to memorize all of these values. What's very important, number one, is that you know how to use this table. I don't want folks to misread what a particular signal corresponds to. But more importantly, we're going to create our own table of values kind of based on importance, what's most useful for interpreting IR spectra. And with practice, you are going to know some of these values. So although I don't expect you to memorize every single value on this table. I do expect you to get enough practice interpreting IR spectra that you do get to know many of the important signals. On this slide, we have a few sample spectra that I wanted to take a look at to be able to compare some of the features. So the first one is for hexane. The second one is 1-hexene. And the third one, I'm going to draw it this way, is 1-hexine. Let's start with this one. So this is an alkane, and so there are no functional groups. Thinking about the bonds that exist in this molecule, we have carbon-carbon bonds, more specifically, carbon-carbon single bonds, and even more specifically, it is a carbon that is sp3 hybridized bonded to another carbon that is sp3 hybridized. In addition, we have carbon-hydrogen bonds. More specifically, it is a carbon that's sp3 hybridized bonded to a hydrogen. Let's focus on, here's 1500. So to the left of that is the diagnostic region. And what we have here is a few peaks. When we mentioned zones, we said that this is where we're going to find bonds between hydrogen and some other atom. So this group of signals must be due to the CsP3 connected to the H. The carbon-carbon single bonds, in terms of zones, we said that that's going to be in here. We don't really see anything that's very clear, and so this is not going to be very useful. We do have a couple other signals here. Now, because this one is pretty empty, these kind of stand out, and these are some bending vibrations. So in some textbooks or on some tables, they will point out the CH3 or CH2 bends, but although they're noticeable here, they're not really easy to pick out in the other spectra, so I don't worry about those. You don't have to either. Now, if we look at the next spectra, so here we have our alkene, but we also have lots of alkane. So notice we have this group of peaks. Well, down here, we have a similar group of peaks. So just below 3000, we have some signals. This is still the CsP3 connected to an H. And down here, this is still CsP3 connected to an H. What's different is this signal here that corresponds to an sp2 hybridized carbon connected to a hydrogen. And here we have an sp hybridized carbon connected to a hydrogen. So this one was a CsP2H, and this one is a CsPH. So we can think of this as an alkene hydrogen and this as an alkyne hydrogen, but I prefer to think of it as sp3 hybridized CH, sp2CH, or spCH. Notice in some cases we are pointing to a single peak, and in some cases we're going to look at a group of peaks. And that's common when we're talking about carbon-hydrogen, because in organic molecules we're going to have a lot of carbon-hydrogen bonds. So in general, you don't have to worry about trying to identify these different ones, but just be able to group together the ones that correspond to a particular type of bonds. The other features that we see in the lower two spectra that we don't see in the top one would correspond to, in this case, the carbon-carbon double bond. So that is this signal right here. And then the carbon-carbon triple bond is this signal right here. The fingerprint regions look different from each other, but these are not really important peaks that are necessary to interpret. So this completes our introduction to infrared spectroscopy, and next we're going to start looking at characteristic absorptions.